Hi class, we are now on 9.7. This is sort of a long lecture compared to the other ones, but I have a lot of examples to try to help you understand this. Okay, so electron configurations, again, this is kind of a way of giving an address to each element. And we can determine how many electrons, because soon we're going to start dealing with elements, atoms, that are not neutral. That means there's an imbalance of protons and electrons. So right now we're just learning about neutral atoms. So an electron configuration shows the occupation of orbitals by electrons for a particular atom. So now we're going to start to write this out. And that's based on the orbitals that we just covered in the last section. So we're looking at ground state atom, a hydrogen atom, and we would write it with the information that we understood from the previous section. So one hydrogen atom can occupy a 1s1 orbital in hydrogen. This means here is the principal quantum number, n equals 1. The orbital is s, and the number of electrons that's held with this atom. So this is 1 electron. So 1s1 is how we say this, 1s1. If, let's say, this was a 2, it couldn't be hydrogen because hydrogen can only have 1 electron, but helium can hold 2. So it would be 1s2. So this electron configuration tells you how many electrons and where they're located and what level they are. So we're going to start expanding out on this. All right, so another way to represent this information is with an orbital diagram. So we have electron configuration, which is this, or we can actually do an orbital diagram. We're going to cover both. This is another way to show the same information, but we use boxes. So the orbital diagram is a ground state hydrogen is simply this, 1s. So think of this as those boxes I was showing you in the previous section, and you put a check mark. It looks like a half check. So it's half and then down. This means an electron, and it means this electron's pointing upwards. So it has 1. So if this is electron configuration is 1s1, this also means 1s1 for hydrogen. So the box represents the 1s orbital, and the arrow within the box represents the electron in the 1s orbital, and it's facing upward. Okay, so in orbital diagrams, the direction of the arrow pointing up or down represents the electron spinning. So the electrons are not standing still, they're spinning, they're constantly in movement. And this is very similar to magnet. When you put two magnets in the same side, they bounce off. No matter how much you try to push them together, they do not want to be near each other. And this is the same thing. Electrons are not stable near each other if there's two positive ends or two negative ends. They have to be flipped, just like a magnet. And that's how we look at this. So remember I told you each orbital can only hold 2 electrons? When you place the electrons in, and there's 2 of them, they have to be in opposite directions. This is called the Pauli exclusion principle, and it states that orbitals may hold no more than 2 electrons with opposing spins. Now, if you put these both in the same spin, it's a very unstable atom, and it's not going to last that way for long. It will try to get rid of that excess energy. So an orbital capacity and electron spin. The Pauli exclusion principle states that each orbital can hold a maximum of 2 electrons. Each electrons in the same orbital repel each other, so that's why they have to be in opposite directions. So that they have magnetic spins in opposite directions, allow them to be able to be in that same orbital together. So again, magnets together, the same ends, they don't want to be near each other. You'll feel that push against each other where they want to be far away. But if you flip them, then they will go together easily. So here is a table of electron configuration, energy levels 1 through 4. We have more energy levels, but we're just covering 1 through 4 right now. So let's take a look at what we have. We have a principal quantum number, and the quantum number matches how many levels you have inside. So these are the bedrooms, this is the house. And this is the address, this is how many bedrooms and where you can find these electrons. So let's take a look at energy level 1. We have 1, number of sublevels is 1, lowest subshell is S, number of orbitals is 1 because it's S, maximum number of electrons is 2, total electrons is 2. Energy level 2, we have 2 sublevels, we have 2s and 2p. An s orbital is only 1 orbital, but a 2, or excuse me, let's just keep going. Maximum number of electrons is 2, and we don't have a total yet because we also have 2p orbitals, a 2p orbital we have to talk about. Now 2p orbital doesn't mean one orbital. We have 3 orbitals within the 2p. So that means a maximum number of 6 electrons that can be held, because 2 in each. So a total between the 2s and the 2p is 8 electrons. Now let's take a look at 3. We have a 3s orbital, a 3p, and a 3d. 1s orbital has 1. 3p orbital has 3 orbitals, and 3d orbital has 5. So the 1s can hold 2, the 3p can hold 6, and the 3d can hold 10, a total of 18 electrons for an n equals 3. N equals 2 has a total of 8 electrons. Now n equals 4 has 4s, 4p, 4d, 4f. So we've already covered the d's, the s, and the p's. That's 1, 3 orbitals, 5 orbitals, but 4f has 7 orbitals, which means a max of 14. So when you add all the 4's together, it's a total electrons of 32. Okay, so if we do a diagram, this is another way of doing a diagram to show the energy. So in multi-electron atoms, the subshells within a principal shell do not have the same energy because of electron-electron configuration. So if you take a look here, 3s is not exactly equivalent to 3p, 2s is not equivalent to 2p. That's what this means, is that because of electron-electron configurations, they're not all level. So when you see a 3, that doesn't mean that they're all going to be level. In fact, 3d is all the way over here, 4d is all the way up here. So if you notice 3p, 4s is lower in energy than 3d. So there's this little weird thing. 4p is here, 5s, and then it's 4d. So there's this weird little thing that we have to take care of, is that the energy levels, just because the number in front is for a principal quantum level number, but those subshells in that level are not all equivalent. So the 4s subshell is lower in energy than the 3d, even though its principal quantum number is higher. All right, so writing ground state electron configurations. A helium atom has 2 electrons. So we already looked at hydrogen. Let's look at helium. Helium has 2 electrons, so it's still on the n equals 1. The principal quantum level has 1s subshell, but it can hold 2. So you would either write the electron configuration as 1s2, or orbital diagram with 2 electrons and opposite spins. This is enough. This is the address. This is telling you what element it is. If I gave you just this, you should be able to tell me that it's helium. Why? Because helium has an atomic number of 2. And this can only hold 2 electrons. So this tells you that this is this. This also tells you it's this without giving you this information. So if we looked at lithium, lithium has an atomic number of 3. How do we know what that is? Well, you add all the electrons up. So once you get it to an orbital that can no longer hold electrons, you go to the next orbital, the next energy level. So in this case, we have a 1s2 that has already been filled with 2 electrons, but we still have a 3rd electron. So now we have to go to the next level, which is 2s1. 3 electrons here. If I looked it up, it's lithium. Same thing here. 1s has 2 electrons, and then 2s has 1 electron. Does it matter how this electron is written because it's by itself? No, but we tend to write it up instead of down when you first write them. But there's really no special difference. For carbon, so let's see what's the atomic number for carbon? Well, if we were given just this, 2, 4, 6, carbon has an atomic number of 6. So this is again where we start expanding on those energy levels. Once you fill up 1, you have to go to the next energy level or next subshell. So 1s2, 2s2, 2p2. What does that mean? So if we expand it out in the orbital diagram, we've already filled in the 1s orbital subshell. We've already filled in the 2s subshell. But remember, 2p has 3. And the rule is that you fill them in separately before you put them together. That's lowest in energy. Chemistry is all about the lowest stable energy, and that is the lowest stable energy. So the 2p electrons occupy the p orbitals. They're all equal energy, but we occupy them in single, let's call these bedrooms, before we force anybody to share a room. This is Hund's rule. When filling orbitals of equal energy, electrons will always be filled separately, and with the same parallel spin. So if you write the spins up, they all have to be up. If you write them down, they all have to be down. That's the lowest energy. You can't write one up and one down. That's not lowest in energy. All right, so orbitals fill in the following order. This is how we're going to fill in electrons, in this exact order. This is something you should learn, because this is exactly how we're going to do this. With whatever atomic number we needed to fill, this is going to give it to you. How do I know? Well, helium has 2, so it would be a 2 here. We wouldn't look at the rest. Carbon, 2, 4, 6. It's going to end here. So you see, all of these can hold how many it matches. So this is 2, 2, this can hold 6, 2, this can hold 6, this can hold 2, this can hold 10, this can hold 6, 2, 10, 2, 6, 2. It takes a while. But that's why you need to know how many it can hold. That's going to help you when you have to write out an address for an element. And this is how you write it. So you see 3s and 3p. So we go down here, 2p to 3s. We go back up to 3p, 4s. We always fill in 4s before 3d, 4p, then 5s, 4d, 5p. So it's not all in order. After we hit a certain point, we have to follow it in a certain order. And this, if you memorize this, you will never get this wrong. Okay, so this is exactly why. So we see 1s, nothing more there, 2s. So if you look at a periodic table, this is exactly how it's filled. 1s here, 2s, 2p, 3s, 3p, but 3d is all the way down here. That's why there's no 3d. We hit 4s before we fill in 3d. We hit 4p before we hit in 4s, or 5s, 4d, 5p, and so forth. All of these are elements. And this is going to fill up. These are the noble gases. These are the halogens, and so forth. Okay, so orbital diagrams uses boxes to show how electrons are arranged. Same thing. We would fill it in. We would draw these boxes, and we would just fill it in, knowing exactly this is the information right here. All of these. Okay, so let's take a look here. Fill the orbitals and energy levels from lowest to highest. So we always start with 1s and we expand out. Highest energy level. That is wrong. That should be over here. Fill orbitals within the same sublevel one at a time before pairing. So if we deal with the p's, we fill these in separately before we fill them in together. That's lowest in energy. So lower energy orbitals fill before higher energy. Remember that bookshelf? We start as n equals 1 and we keep going up and up until we can load all our electrons into orbitals. Orbitals can hold no more than 2 electrons, regardless of what type of orbital or subshell it is. When 2 electrons occupy the same orbital, they have to have opposing spins. You can never draw them with the same spins. This is known as Pauli exclusion principle. When orbitals of identical energy are available, all of these are first occupied by single electrons with parallel spins. That would be like the p orbitals. We put them in separately before we add more. That's Hund's rule, and they all have to be in the same spin. Same direction. So this would be a perfect example of Hund's rule. We put them in separately, but we face them all in the same direction. Well, what happens if we start expanding? This is nitrogen. Well, oxygen, we just start expanding them into the box. We have nowhere else to put them. So if we have 3 bedrooms but 4 people, one person's going to have to share a room with somebody else. And it keeps expanding like that. So you see, but when they're all in there, they are in opposite spins until it becomes completely filled, like neon. This is fluorine, and if you count these, 2, 4, 6, 8, 10, this is 2, this is 4, this is 6, that's 10, 2, 4, 6, 8, 9, 2, 4, that's 4, and that is 5, that's 9, 2, 4, 6, 7, 8, this is 4 and 8, 4 and 4 is 8, they all match the atomic numbers. So this matches this. The only difference is that with the P, we leave it not expanded. So we can write 3 here because it's one of those things that you're supposed to know there's 3 orbitals and not like this. So you see it's 6. That's because there's 3 orbitals. We can have a max of 6. So electron configurations, chemists use notation called electron configuration to indicate the placement of electrons in an atom. So I've kind of already covered this. Shows how electrons fill an energy level. So if we look at this one for carbon, this means we have a 1s2, 2s2, and 2p2. That's how you read this, if you're asked to read it. We're now going to show an abbreviated way. Eventually I'm going to get to abbreviated. So here, these are just, remember I said I had examples. This just shows you the atomic number, the element, the orbital diagram, and electron configuration, and I have several of them. So you can see. Now there's an abbreviated way to write these, because after a while, this periodic table has very large atomic numbers. So there's an abbreviated way to write these, which is a shortcut. And if it's not specified how you have to write it out, then both are accepted. But if it's asking for an abbreviated way, electron configuration, you have to write it out with the abbreviated. Or if it's asking for just electron configuration, I would always make it, if it's not specifying, this is where it's tricky. If it's not specifying it, you can write it either way. But usually when they mean electron configuration, they mean the whole thing. So again, here's more. I'm going to show you how to do the abbreviated way. But these are more, this is why I have so many slides. I'm breaking it down. Okay, so nitrogen atoms are found in amino acids, proteins, and nucleic acid. Draw the orbital diagram for nitrogen. Nitrogen's atomic number is 7, which means it has 7 electrons. So we are given orbitals of 1s, 2s, and 2p. So how do we fill this in? Very simple. You just start filling it in until you can't fill it in anymore. And in this case, we already filled in these, and we still had 3 left, so they have to be all in the same direction. That's it. So when you understand, if we go all the way back here, if you memorize this, and you know that you have to expand some of these out, you will have no problem filling in the diagram for these, any of these, because the what I'm asking you to memorize doesn't change. Okay, so then we go, here's 3s block. And that shouldn't have moved there, but it moved. Again, there's more, so I'm giving you everything here. Electron configuration, here's more. This is showing you everything that will help you. So this periodic table matches everything here. This is, okay, so 1, 2, 3, 4, 5, 6. So this actually cuts off 1, 2, 3, 4, 5, 6. No, it doesn't. Oh, because they have helium over here in this one. So all of these represent where they are in here. So 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. That's what these are. Remember, there's 6 electrons. P can hold 6 electrons. So that's what all of these are. This is a 3p1, 3p2, 3p4. Same thing. 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. They all have a specific address and where they need to be. All right, so electron configurations 4 and above. This thing moved again and it shouldn't. So I'm still giving you some here so you can see more examples. All right, but there is something weird that happens. If you see chromium and copper have half filled. So what they found, so if we were to follow this, you can see that this is a 4s1 3d5. What it would normally be is we would take one of these off and it would be 4s2 like this, 3d4. But when they found is that by leaving having 4d orbitals when you have 5, it wasn't low in energy as it should have been. But when they removed one of the orbitals, electrons from an s, and filled in all 5 orbitals, it made this lower in energy. So chromium is a weird one, that this is electron configuration that doesn't match what's before it or what's after it. Same thing happens here. The same exact thing. They pull, it doesn't match what's before, it doesn't match what's after. It moves one of the electrons from the 4s orbital into the 3d, and it's actually lower in energy than what it would be as a 4s d9 orbital. So you can see here's more electron configuration. So I'm giving you as much as I can here to help you understand. So we use the sublevel blocks on the periodic table to write the electron configuration for selenium. So if we wanted selenium, we need to locate the element on the periodic table. Selenium has an atomic number of 34. It's in group 6A and period 4. The period number is also the principal quantum number. So that helps. When you know what the period is, it's going to tell you what the principal quantum number. Write the filled sublevels in order going across the period. So when we have to write this out, we have to fill in everything. So this is actually a little harder. But remember I told you to memorize that one thing of all the levels? If you write it out, you don't need to do all of this. Write it out and start counting out what you have. So this is 34, right? So this is 2, 4, this is 10, 12, 18, 20, 30, 34. If you memorize that long electron configuration in the correct order, and you can keep in mind the 2 weird ones that we just learned, I don't want to say weird, but lower or odd ones that stick out, you won't have to struggle filling and looking at a periodic table and doing all this. So as long as you know the atomic number and it matches with the math, you're good. So this is also showing you, this is a 2s1, 2s2, 3s1, 3s2. This is a 3d1, 3d2, 3d. So all of these have an address to all of them. Okay, so let's start looking about abbreviations. Once you're familiar with electron configuration, you can do the abbreviation. So we look for an element needed for an electron configuration. Look for the noble gas that is in the row above and write the chemical formula in brackets. So write out the remaining configurations. Let's use aluminum. So if we look at aluminum, aluminum is, where's aluminum here? It's here somewhere. There it is. It's 13. Okay. So if we write out this is a all P's, right? So this is 3P1. So I should end at 3P1. This is 3P2, 3P4. Whatever the period number, that's the quantum number. I forgot to mention that. All right. So it's going to end in a 3P1 if I did this right. So here we have 1s2, 2s2, 2p6, 3s2, 3p1. This should match 13. 2, 4, 6, that's 10, 12, 13. All right? But what if I could make it a little easier and just focus on an abbreviation? So it says to go to the noble gas right before. So we can't go past it. That's too many electrons. But what we can do is go to the level above, and neon. Neon is 10. So I can kick out 10 electrons and only focus on the remaining ones that get me to here. So that's what this is. If I put neon in brackets, it automatically means 10. So I don't have to do what's in pink because the pink here covers that. Now make sure, again, whatever's being asked of you, make sure you can actually do this. If it's specifying it in a certain way, you need to do it in the long way or in the abbreviated way, whatever it's specifying. But in this case, I can kick out doing all this, write neon, and then because neon's here, these are s orbitals. This is 3s1, 3s2, 3p1. And I can just write the remainder. And you can do this for any of them. So let's say I wanted to write neon, but I'm asking for the long way. I have to write this all out. But what if it's asking for the abbreviated way? I just simply write it in the brackets, the concentration brackets with neon. And concentration brackets, not parentheses. The square brackets. Okay, so here's that weird exception on those two that I was talking about. And these split, I apologize. This should not have a space and this should not have a space. When I save these, sometimes they don't save right, and I don't know why. 3D sublevels. I have some worksheets, and I believe one of them is not correct, or it is correct now. I can't remember if I fixed it. If I did not fix it on my worksheets, please let me know so I can go in and make a notation. But know that there's still an old way of doing this where they don't count this. Don't follow it. I try my best to find worksheets that keep everything up to date, but some of them are not. And if you can catch it, that's great. That means that you learned it. I can't remember if I changed them out or not. For chromium, this is what we're talking about. We take the one electron that's here and we move it to fill in the half filled. This is lower in energy than if we move one of these electrons and puts it in a filled one here and have 4. Same thing here. If we move one out, instead of having 9, we have 10, and this lowers the configuration for this chromium, copper. So this is chromium, this is copper. Whatever's the noble gas prior to it, we can put the abbreviation, and then we have to just work with whatever gets us to the end where chromium is, and the same thing with copper. Okay, so use the periodic table to give the symbol and name for the element with this. Remember I told you these are addresses, so all we have to do first, add them up. 2, 4. Well, if you wanted to actually look at this in a different way, let's look at it a different way. These are periods, right? 1, 2, 3, 4. Remember I told you that the last one, whatever this is, that's the period number. That's the principal quantum number. Period number and principal quantum number equal. So I'm going to cheat a little bit before I add this up. 1, 2, 3. So I am 3, but remember this is a 3D. So we actually have to go down 1 because this is 3s and this is 3p. And remember, a periodic table is not going to give this to you. So you're going to have to make sure that you understand this or print out a copy of this. But 3D's here, okay? It's 7. So 1, 2, 3, 4, 5, 6. Hold on, I miscounted. 1, 2, 3, 4, 5, 6, 7. So I'm going to say this is cobalt. Let's check, which is 27. So 2, 4, 6, that's 10. This is 12, 18. This is 20, 27. If you know how to read a periodic table where these orbitals should all fit, you can verify it by just adding them up. So if I'm right, it's cobalt. I was right. 1, 2, 3, 4, 5, 6, 7. 3D, principal quantum number, but with these, they all go down a step. So even though this is principal quantum number 4, which is period 4, there's a 3D. This is period 5, but there's a 4, 6, but there's a 5, and so forth. Write the electron configuration for the following elements. I'm just going to cheat and go right through it. So I give you the abbreviated, and I've given you the actual long ones. So the first thing, figure out the atomic number. Once you know the atomic number, you can either take the shortcut way or you can spell it out. But make sure you are comfortable with you're doing the abbreviation. You fully understand how to do that. You have to take the one above, not the one that's even on the same level. This is too many electrons here. This atomic number is passed. You have to go the one above, which has less electrons. Silicon. Silicon is right there. So neon was first, and then you can just fill in the rest. Here it is. Oxygen, same thing. Okay, write the configuration, write the electron configuration for the following elements. I don't know what happened there. It cheated or it repeated the, I don't know. This is the same thing. This slide shouldn't be there. Okay, so electron configurations in the periodic table. Now there's one more thing I have to cover here. We have a whole bunch of electrons, but they're not, some are more special than others. We have valence electrons and we have core electrons. And the valence electrons are what make chemistry chemistry. The core electrons, they're just there. So valence electrons are electrons in the outermost principal shell, the principal shell with the highest principal quantum number. So when we look at this, we're looking at, this is a 3, this is a 3. So this level here is our valence electrons, and everything before it is not. This means that these valence electrons here are involved in all the chemical reactions, and these are staying closest to the nucleus and do not interact with what we need. And that happens with all the elements. All the elements have a certain amount of valence electrons and core electrons. So electrons that are not in the outermost principal shell are called core. They stick close to the element, and they have nothing to do with what we do with chemical reactions. When we start dealing with chemical reactions, it's only the valence shells, valence electrons that take part. So silicon has 4 valence electrons. We have 2 in the S shell and 2 in the P shell. Those are N equals 3 and 10 core electrons. So usually what we do is when we write this out, we will put dots for the valence electrons around it, and the core electrons are implied with just the chemical formula. We don't draw all of them out. The 10 are never drawn, just the valence ones. When we start doing electron dot notation, we would do 1, 2, 3, 4, 4 electrons to show there's 4 valence electrons that are involved in this chemical reaction. So selenium has 6 valence electrons, and so if you look here, let's see, we have, here's a 4 and a 4. So even though 3D is right in between, it does not play a part because it's a lower principal quantum number. So selenium has 4s and 4p, and the rest of it is considered a core electron. So if we had to draw out the electrons around this, we're not drawing out the 28 core electrons. We're only drawing out the 6 valence. So we would do little dots. 1, 2, 3, 4, 5, 6. So 6 valence electrons. Okay, so you can do a search on Google for periodic tables and electron configuration, and you will get the valence electron configuration for every element on the periodic table. It looks really busy, so that's why you don't see all this here. You're only seeing the first 3 levels. But you can see as it goes up, you see how it starts expanding with each number until you get 6, because that is all you can have. You have 2 from here and 6 here, that's 8. 8 valence electrons is what's always wanted around an element to make it stable. The only difference is the first level, which can't have that. It's called a duet. So anything here always wants to have 8 electrons around it. We call that an octet. And helium and hydrogen want a duet. That allows it to be happy. And how does hydrogen have a duet? Well, it joins with itself, and that becomes two hydrogens together. Hydrogen gas is two hydrogens together. We call that a diatomic gas, and it has two electrons. Okay, so here I told you it's like really busy, but I found something that you can see all the addresses for each element. And that's it.